Hello, everybody. Welcome to this Tech Week webinar on predictive analytics. Just a little bit about the format of the session today and a bit of housekeeping. You're all muted at the moment, probably best to stay that way and communicate in the chat window, which should be at the bottom of your screens if you'd like to get our attention. We'll be monitoring that. We are recording this session today to make it available afterwards for anyone that wants to see it. Shortly, I'll introduce Adam Lyness and Tom Blomfield, who will take you through the webinar, which will take about 15 to 20 minutes, and then we'll take some questions at the end. So we'll do this using the chat as well, so feel free to have, if you've got any questions, type them in there at any time. I'll collate those and interrogate Adam and Tom with them at the end of the session. As for who we are, I'm Dave Sanders, Managing Director and Co-founder of Intranel. We're a software development and consulting business based out of Christchurch. We've been working in a wide range of areas and industries over the years, but first dabbled in machine learning neural networks way back in about 2002 when we were looking at image recognition for video security systems. We've got back into more AI, machine learning and predictive analytics activities more recently. And things have certainly changed in this area since the old days. Tom and Adam have been leading this sector of the business here at Intranel. Adam's a co-founder of Intranel and Tom's our technical lead, but they're both all around excellent people to talk to about pretty much anything tech-wise. I'll hand over to them now to take us through the talk, and just remember, any questions, send them through the chat and we'll get through as many as we can in the time available. So Adam and Tom, over to you.
Yeah, thanks, Dave. Hi, everyone. I'm Adam, and I've also got our technical lead, Tom, with me. So my role is mostly business development. So while I'm a bit of an enthusiast for machine learning, Tom's really going to be the one who can field all your tricky technical questions. So if you chuck him in the chat window, he'll get busy Googling while we work through the presentation. So today we're going to focus on predictive analytics, a subset of machine learning with potential to improve a lot of business processes through better use of data. On the agenda, we'll cover what it is, why it's being increasingly adopted, and provide some examples in a case study just to give a bit of context. After that, we'll look at finding use cases for your business and what you'll need in place to test these before outlining a process to run machine learning experiments and assess business value before committing models to production. So that should all take under 20 minutes, and we can do 5 to 10 minutes of Q&A at the end. And as Dave mentioned, feel free to post those questions or comments in the chat window. So predictive analytics essentially is about using data to help predict the future, in particular an output variable of interest, whether that be future retail sales or pedestrian traffic. Analytics in general, or descriptive analytics, helps contextualize data and provide insights. Predictive models can help with this more general case too. So where predictive analytics comes in handy is when patterns are too complex for intuitive human models to work, or where humans miss outliers. For instance, it's really valuable to know in advance if we're likely to see a big surge in demand that we wouldn't otherwise expect, and we can take action to mitigate those impacts. Predictive analytics, it's a field of machine learning or artificial intelligence. AI is also a powerful tool for computer vision. This isn't going to be a focus of this talk, although AI, of course, can generate huge amounts of structured data that feeds into other analytic pipelines. Predictive analytics models typically rely on automated statistical regression, although these models can use deep neural networks, and we'll touch on that later. And just when we're on top of predictive analytics, the trendy new term is prescriptive analytics, which just shifts the focus to using data to find the best course of action and emphasizes those actionable insights instead of just data monitoring. In essence, it's really just how predictive analytics should work. I'm kind of a little bit uncomfortable about the term prescriptive because it sounds a bit draconian, like we're all about to be enslaved by data. So the statistics that predictive analytics is based around has been around for a long time. The growth in this area is mostly being driven by new tools and increasing automation that makes extracting value from data much faster and more cost-effective. On top of this, organizations are generating more data that can be leveraged, and there's a general trend towards cloud services making access to this data much more efficient. All three of the major cloud service providers provide data-focused machine learning services that interface easily with their data warehouses. Finally, we're seeing more automation in the ML ops space, and this is making it easier to integrate and maintain models within your existing infrastructure. So here's some example use cases, just to add a bit of context. You can see from these that the common theme really is around demand prediction, although your output variable could be anything you want to predict, given a set of related input data. At a certain level, it's worth mentioning that systems become so complex or noisy as to be fairly unpredictable. One example is trying to predict share prices. We actually tried something a little bit similar to this a few years ago, and obviously if we'd been able to do that reliably, we probably wouldn't be here today. So identifying when it makes sense to invest in building and testing a model can be a little bit nuanced. So often people come to us when they have an intuitive sense that they should be able to accurately model useful predictions from the data they have, but basic approaches like a running average are maybe limited in effectiveness. Equally, an organization might be sitting on a bunch of data and be keen to explore how value could be extracted. So prior to charging in and building models, we'd recommend exploring the data you have to help identify how predictive models could actually support your business strategy. This is a process we can help with, because if you just go ahead and build a model to predict something accurately, it doesn't mean that it'll necessarily add value. If it doesn't lead to change, better understanding, or actionable insights, then there's potentially limited value there. The good news is that it's often possible to test the model and assess value without burning a bunch of cash. You can sign up to some cloud services, maybe grab your best Python developer and run some experiments to see if you're onto a data goldmine before committing to production. And even just going through this exercise will also provide a bit of a health report on your level of data maturity and help identify trends and behavior within data sets, even if you don't end up fully productionizing the outputs. So in the ML space, both data science and data engineering skills can be useful. And these can be accessed on a contract basis through providers like Intranel or bought in-house as needs evolve. And if you're looking to develop internal capability or test models, both UC and Waikato have really good data science programs, and they can provide both graduates and expertise for longer term projects too. Okay, time for a deep dive to run through the whole process of developing, testing, and deploying a model. So once we've identified a business case for a specific prediction, we can look at what kind of model we need. Predicting, say, length of hospital stay may be based on non-stationary factors like age and comorbidities at admission. The inputs and outputs, in this case, say length of stay in days, is a single number. This type of stationary data model tends to be less complex to build and evaluate. Typical business problems, however, require predicting a series of non-stationary data points over time, like sales, share price, passenger arrivals, and so on. We call this time series forecasting, and it's usually more complex with higher data requirements. Next up is figuring out whether we want to do univariate or multivariate analysis to begin with. For a time series model, univariate analysis solely uses past behavior of the variable you want to predict to model its future values. It looks for past periodicity and patterns in this variable, and it's actually good for many types of data, but will break down when you have irregular, unexpected events that don't necessarily have that clear and identifiable pattern. Multivariate analysis can address some of these shortcomings, but requires manually adding additional variables or features to the input data that can't be derived from the output variable. For instance, if you run an ice cream truck, you know that the weather forecast will likely have a big impact on your sales tomorrow, rather than just building an estimate based on your sales today. In this case, a temperature forecast variable could be added to the model. And this is a basic example of what we call feature engineering. Multivariate models also allow easier exploration of what-if scenarios, as you can train using data from previous irregular, high-impact events, and then test their impact when added to a current data set. For instance, if you've modeled foot traffic as a feature impacting sales for a retail space, you can test the impact of a scheduled public event on predictions by feeding that inflated foot traffic figure into your model. So data wrangling is the process of getting the right training data into a model. And this is usually a good chunk of the overall work. So it requires pulling in data from often multiple sources, cleansing it, anonymizing it potentially, as well as reformatting and removing periods where patterns may be inconsistent. COVID has pretty much managed to create a whole year of inconsistent data that bears little relationship to previous years, so it's a good example of this. And data wrangling may highlight challenges with your organization's level of data maturity. If you've got a bunch of distributed, inconsistent data across multiple silos, then it's obviously going to be more difficult to build good models. It's also worth keeping in mind that there are myriad data sources out there, both public and private, that can be useful, including council data, your NZTA, maybe weather data from the Met Service, and so on. With AutoML tooling, training a model, once you've got your data in place, can actually be the easy bit. Tools will automatically try different model types and identify models that generate the lowest error rates. And this training uses a process of feeding back errors, a process called back propagation. So it just rates on model parameters and iterates over several cycles to minimize the defined error function. Hyperparameters control this learning process. For example, the types of analysis to use, the number of iterative cycles to target, or your target error rates. Feature engineering involves identifying factors that influence our output feature and testing their input on a model. AutoML will provide automatic feature extraction, for instance, identifying that sales from 7 days ago are a strong predictor of sales today. Automated features can be selected or excluded, and features can be manually crafted from other sources, a process essential for multivariate modeling. This type of manual feature engineering allows us to include factors that have a fairly irregular instance, but maybe a major impact on our model. For instance, we may find a model predicting arrivals at a GP's clinic 2 weeks in advance isn't that great until we factor in time-lagged epidemiological data on circulating illnesses, as well as weather data. Once we've tested and evaluated our basic trained models, we need to test those models against new sets of data. So evaluation involves testing a model against new data not used for training. So if a model using data, say for 2016 and 2018, can predict daily time series sales when tested against different data from 2017 and 2019, then there's a good chance it'll perform well on live data for 2021. If this evaluation doesn't yield adequate performance, we can iterate through feature engineering and adjusting hyperparameters to tune and improve our model. And at a certain point, the model is hopefully good enough to justify a business case for rolling out to a production system. So we've got a model, now we need to deploy and maintain it. And to be useful, models need to integrate with business systems. Outputs could be visualizations in Power BI, maybe planning dashboards, anomaly detection, alerts, and so on. In addition to this, data tends to change or drift over time. So most models need frequent automated retraining to remain accurate as these trends change. MLOps encapsulates these processes by defining how machine learning models are integrated within a business context. It includes automation of data connections, routine model retraining, and integrating model outputs with business processes, as well as generating alerts if anything goes awry with the whole ecosystem. Essentially, it's just DevOps applied to machine learning pipelines. Okay, time for a quick case study, just to keep it real after our deep dive. This example is from the restaurant sector for a SaaS provider of a tablet-based POS and menu ordering service. So they've got thousands of restaurants as clients and generate huge amounts of point-of-sale data. They'd like to be able to offer individual restaurants some useful data insights, as well as accurate demand forecasts to help them with food ordering, inventory management, and staff rostering. So it turns out that predictions for individual restaurants are harder than for a large group because the impact of localized irregular factors at the individual restaurant level plays a much more significant role, whereas these tends to average out as you add more and more restaurants to a group. Furthermore, most of the business value lies in detecting these outlier events at the local level because these drive decision making much more than, say, a plus or minus 10% variation in demand. For instance, if a proprietor knows in advance of the size of a blip she can expect from a holiday weekend, she can make operational decisions to avoid running out of food or putting undue pressure on staff. In this case, multivariate models with additional localized features like weather, foot traffic, and public holidays are necessary to add dimensionality and reveal patterns that univariate analysis can't at that local level. Getting these features right requires feature engineering as well as domain knowledge. For instance, not every public holiday is equal in terms of impact, depending on the sector we're operating in. Another example that requires an element of judgment, say, is whether to model the impact of Christmas Eve across multiple restaurants in a region, or to do this at the individual level across several years of data on the basis of those highly localized impacts. The good news is that AutoML tools make the process of experimenting here, of including and testing new features and hypotheses fairly quick. They can quickly tell you whether including weather data, for instance, is going to improve that model accuracy significantly. So it's worth commenting on model visibility. We've all seen examples of ML models that demonstrate implicit bias, and this is usually based on the data they've been trained with. One example from a few years ago is Amazon realizing that their algorithm for hiring employees was biased against women. And the underlying reason for that was because the algorithm had been trained on resumes submitted over the past 10 years, and the vast majority of applicants in that period were men, hence it tended to favor men over women. And one advantage with predictive models developed using the more typical automated regression methods is that these are white box, and that we can see the impacts of different feature variables and how strongly they impact predictions. Deep learning neural networks, on the other hand, can be used for solving similar problems, or they don't offer the same level of visibility. And we haven't showed you many dashboards because they tend to be pretty esoteric with lots of data all over the screen, but I think this is from Tom, the Azure ML tools, and it actually shows one of the dashboards there where you can see the relative impact of different features or variables down the bottom.
Yeah, correct. It's the feature importance dashboard from Azure AutoML.
Cool. So in terms of choosing what platform to build on, all the major cloud services have solid offerings in the analytics space, and there's also a number of fairly well-funded full-service independents like DataRobot. In general, you're pretty safe to build ML models within the cloud environment your data already exists in and that you're most comfortable with. And on occasion, of course, there's BYO models and hosting that leverage a custom set of tools do have their place, especially if you've got complex requirements. So just addressing a few other challenges and maybe some general comments. We often get asked how much data is enough to build models. That can be a bit of an open-ended question. Enough data generally means sufficient for clear patterns to emerge to the AutoML tools, even if these are complex and they may look fairly random if you're just casually observing the data. And sometimes experimentation is required to figure out that number, although a data scientist can often estimate a pretty good ballpark figure. Too little training data risks overfitting a model, although you're normally going to find out if this has occurred when you test your model against fresh data that it hasn't seen before. Modeling infrequent events such as New Year's Eve that we mentioned before may require a few years of data to actually build a clear pattern to measure that impact. And of course, by the time you've accumulated sufficient data for an amazing model, the underlying trends may actually have drifted over time. So it is worth mentioning that automatic machine learning, the tools, they can't do magic, and they still need enough training examples for a clear pattern to emerge. Another issue to note is that models often optimize for accuracy, but predicting outliers may in fact be more useful. So going back to our restaurant example, you don't necessarily care about a plus or minus 10% daily fluctuation in patronage, but you do want to know if you're going to get swamped on Tuesday because it's a public holiday with fine weather. So as a general rule, placing an emphasis on actionable insights rather than just data monitoring for the sake of it is always going to add more business value. So data wrangling can be complex, and it's worth mentioning that a good analytics strategy is intimately linked with your overall data strategy, because models are going to be much harder to build if data is spread across multiple silos in different formats. The shift towards moving data to the cloud is certainly helping making this process easier. The good news as well is that AutoML platforms are starting to perform automatic data pre-processing, and that assists with profiling, outlier filtering, missing values and formatting, so you can get solid results ahead of our utopian level of data maturity. So that's about it from me on the core presentation, but I'll just quickly summarize those key points. If you're sitting on big data sets and thinking there may be gold and then there are hills, it's definitely worth taking a closer look. Likewise, if you've got a pressing business problem that requires predictions and you think your data would enable this, you're probably right. At this point, the process becomes one of wrangling that data and spinning up a test platform to explore some models and see what kind of results you get. If they're less than ideal, contemporary tools make iteration through feature engineering and parameter tuning efficient, although you can't escape the need for good domain knowledge. A bit of data science support may help at this point too. So once your models are looking amazing, you still need to integrate them into your organization to actually deliver those actionable insights, and your overall business case may be dependent on your level of data maturity. This MLOps process can be the most complex and time-consuming, particularly if you want to fully automate the entire flow of data. Fortunately, you can usually approach these challenges with incremental improvements, and this is an area with rapidly evolving tools and increasingly domain experts available to help. Okay, that's me. Thanks for your time there and attention today. Maybe I'll pass that mic back over to Dave, and we can run through some of those questions that may have come through.
Excellent. Thanks, guys. Right, on to question time. Anybody there, please use the chat option in Zoom if you can. If you haven't found where that option is in Zoom, I'm not sure what you've been doing over the last year, but it's down the bottom of most screens. But if you prefer, you can also unmute yourself, I believe, and ask directly if that's better for you. Any questions for the guys?
So, did we cover it amazingly well, or is everyone just confused?
Here we go. First question in. What tools do you use for data masking?
Oh, that sounds like one for
Tom. We haven't dealt much with that here. Because the data, so I'm currently working on a healthcare project, so it would seem like we'd need to do a lot of, I guess, data obfuscation of things like PII data, but the data we're dealing with is normally already aggregated to the level that where we're not needing to deal with that. We've looked at doing data masking or obfuscation with PII data in the legal space using the NLP, the natural language processing tools that Azure has out of the box that flags PII data if you pass it structured or non-structured text data.
Cool, thanks, Tom. Next one here, someone's just asked a question about if you could explain the difference between data science and data engineering for us.
Sure, yeah. So I guess data science is the domain of understanding your data. So using statistical tests to figure out if there are correlations inside your data that matter, and data science has encapsulated the modeling domain now as well, so the machine learning side of it. Data engineering, I put more as the software development and operational, the MLOps side. So building those MLOps pipelines, taking the data that you have as a data mature business or otherwise, and passing them through to the models. It also involves, as Adam touched on, models aren't a thing that you create and then you leave for the rest of the time. They have their own life cycle and need to be maintained. So data engineering for me also includes the MLOps monitoring of those models. It's really the data science and data engineering is a collaboration between more statistical understanding of the models and the software development process to productionize and make use out of the understanding.
Yeah, and I should say you can, with modern tools, you can, software engineers can train up fairly quickly to be able to do some basic data science and test hypotheses and build basic models. But depending on the level of complexity, a data scientist can help tune those models better and add a lot of nuance into that process. So, it's often good to involve someone with that high level of experience when you do have high levels of complexity.
Great, thanks. Next question, how frequently do you run into data gaps and how do you work around them?
Yeah, so I can jump back into the healthcare space as a good example of this. So you might have really small gaps in your data, which would be from missing data coming through a data import process, or data wasn't recorded at a particular time for, let's say, operational reasons. In those cases, we can what's called impute the data, so that we can assume that if we've got data points around that time, we can figure out the shape of the data in that time and basically artificially generate it. That of course only really works for when we have missing data in really small gaps of time, because if it's anything large, then it becomes harder and harder to, we need to build a prediction model itself to start imputing our data, which wouldn't make sense. I refer to the healthcare space because we've had this, the whole world has had this with COVID, a huge gap of, it might not be missing data, but in terms of the standard operational shape of a hospital, it no longer makes sense. So in those cases, and there's many more cases of this in other industries, we need to go back to the business problem and what we're predicting. So in the COVID case, what we could say is, let's assume that once COVID's passed, we enter a state in our hospital system, which is similar to what it was like back in, a pre-COVID era.
I think what you're saying is train your models on 2019 and not 2020.
Basically that, right? Or at least make use of some of that data. So yeah, to answer your question, or to wrap up my answer, for small gaps, we can insert artificial data, and for large gaps, we look at the business case and figure out where we can grab other sources of data to use.
Excellent. Thanks, guys. That's the last question I can see. If anyone's got anything else, ask quick. Oh, here we go. There seems to be a fair bit of management hype in the space. How important is it for medium-sized companies to invest in machine learning, and how can they avoid getting lost in the journey?
Yeah, that's an interesting observation. So I'd say, like any fast evolving space, it's like, yes, there is going to be a bit of hype, although if you look at where it is on the hype curve, it's definitely got to the point where it's actually genuinely useful in many cases. And I guess, this used to be the domain of fairly well-resourced large organizations, because you can be reasonably confident, say, that Air New Zealand's been doing pretty complex predictive analytics work on travel demand for many years now. But I guess what's changed is it's becoming more accessible to small and medium-sized businesses because of those changes in the availability, the accessibility of tools. The next step, of course, is if you're a small and medium-sized business, you may or may not have access to sufficient sized data sets to be able to build good models. So I guess the general comment is the tools and the opportunity are now accessible to smaller businesses, but you've got to exercise some caution and make sure you've got sufficient and useful quantities of data before you start building and deploying models. I mean, that's just part of the discovery or exploration process if you think maybe there's some value in there.
Excellent. Thanks, guys. We'll probably wrap that up here unless there's any very last minute questions. So although if you do have any further questions, feel free to send them through to us. You can reach us on email, give us a call, whatever suits. I believe are we planning on sending out the slide deck, Adam?
Yeah, we can probably do that at some stage.
Yep. And there will be a recording of the session, which someone will send out as well. So thanks very much. It's been great to have you all along for this Tech Week session. I hope you've been enjoying the program this week, and we'll let you get some lunch and have a great afternoon, everybody.